Okay, class. This is the last topic in the memory organization unit. Let's talk about virtual memory today. To just give you an idea about the virtual memory, just think about this. Your typical computer has a RAM of 4 to 8 GBs. Now, typically a movie comes in round about 1 GB. Let's do an experiment. What we can do is we can install 3 or 4 or 5 different media players in our computer, and in each of those media players we can start a different movie. Or what we can do is we can start 2 or 3 or 4 different instances of the same media player and load a different movie in each of them. At the same time, I can also start, let us say, MS Office like MS Word and MS Excel. Then you can also start up a game and some other, let us say, audio player and things like that. You can open up a number of softwares. You can open up all these softwares in different windows of your computer, right? And then obviously the operating system is also loaded in your computer. So if you add up the sizes of all the files that you have loaded up and add up the portion of the memory that is being consumed by the operating system, you'll be surprised to know that this sum might come even more than the amount of total memory or RAM that you are having. Now, how is it possible? We also know that your computer cannot work directly on the physical storage. It has to bring everything into the main memory before it can start working on the data. So how is it possible for my computer to bring more data into the main memory than is the size of the main memory? Now this is made possible with the help of the virtual memory. Now what virtual memory? Virtual means not real. What virtual memory does, it gives a feeling of having even a larger amount of main memory to your computer. Now this virtual memory is present in almost all the computers. If you are having a Windows based computer, you have this in the form of a page file or the actual virtual memory by the same name. If you have ever installed Linux, you might be knowing while installing Linux, you install a special partition which is called the swap partition. Now that swap partition is the virtual memory. You can even change the way your computer is using virtual memory or how much virtual memory your computer is actually using. But that is a comparatively risky process. I'll tell it to you. I'll tell about it in a short while. So what virtual memory is? Virtual memory is essentially, please listen carefully, virtual memory is essentially a portion of your secondary storage that your computer treats as a part or as an extension of the main memory. So although your main memory is smaller in size, but along with the virtual memory, this virtual memory, it seems to your computer that you have a larger virtual memory. Say for example, your computer may have a 1 GB RAM, and if you are using a 4 GB virtual memory, then for your computer you are having a 4 GB of RAM. So the same thing that I have already told, the virtual memory was developed to give programs a larger memory space than the system's main memory. The appearance of larger address space is realized by using much slower disk space. Now the working of virtual memory, the basic idea of how virtual memory is managed is somewhat similar to how we are using cache memory. If you remember, in the case of cache memory was smaller, main memory was larger, and we said that the cache memory is divided into blocks, main memory is divided into blocks, the size of block is same in both the cache memory as well as the main memory. Then I also said that the CPU always generates an address for the larger memory. In that case, in case of cache memory, the larger memory was our main memory. So the CPU was generating an address for the main memory, which was then mapped to an address of the cache memory. Now let us map everything down to virtual memory. Here the virtual memory is larger as compared to the main memory. Now the virtual memory is once again divided into blocks. The main memory is also divided into blocks. The size of the block is same in case of both virtual memory and main memory. And the CPU is once again generating the address for the larger memory. But now the main memory is the smaller memory. The larger memory is our virtual memory. So the CPU will now generate an address for the virtual memory. And then we will have to map this virtual memory address into the address of the main memory. How that is done? We normally do it with the help of a very simple process, which is the mapping table. So let us now see how this virtual memory actually works. Now, the virtual memory, basically the size of the virtual memory, as I said earlier, size of the virtual memory is larger than that of the main memory. So once again repeating, the address that is generated by the CPU is for the virtual memory. And how things are done is, the CPU or the computer, when it is loading the programs, loads the programs in the virtual memory. Once again, please remember, your computer can load the programs in virtual memory, but for performing any operation, it has to bring the data or the program in the main memory. So although virtual memory can be used to give a illusion to the user or to the CPU that it is having a larger memory than is actually present, and it can also help your CPU in loading more amount of data in the so-called memory. But for performing any operation, the data or the program has to be brought into the main memory. So what happens is, the program is loaded completely into the virtual memory, and then pieces of the program, one block at a time, are brought as and when required in the main memory. So whenever the CPU requires any data or any word, that word is brought from the virtual memory to the main memory. This works similar to what is happening in the cache memory. Even in the cache memory, the data was brought in from the main memory to the cache memory so that it can be provided at a faster rate to the CPU. Similarly, the complete program is in the virtual memory, and then this data is brought from the virtual memory to the main memory as and when it is required. Now, the address space. We have two types of addresses. One is the address space, which contains the virtual addresses, that is the addresses in the virtual memory, and then we have the memory space, which contains the physical addresses. These are the addresses. Physical addresses are the addresses which are used actually for the main memory. And these virtual addresses, these are the addresses generated by the programs, and these addresses pertain to the virtual memory. As you can see over here, the virtual memory is larger as compared to the physical memory. So obviously the address that is generated for the virtual memory will also be larger as compared to the address that is required for the physical memory. So we need some sort of a mapping to convert the larger virtual memory address into the smaller physical memory address. This is a simple example to show that we are assuming that our main memory capacity is 4 kilowords. 4 kilowords means we require 12 bits to specify a physical address. And let us say our auxiliary memory or the virtual memory is 1024 kilowords. That 1024 kilowords means there are 2 to the power 20 words, and we require 20 bits to represent all these words. So our virtual address is of 20 bits and our physical address is of 12 bits. Now how do we do that? As I earlier told, that the virtual memory and the main memory are both divided into blocks, and the size of a block is same in both the virtual memory and the main memory. Remember what we said in the term when we were talking about cache memory. The cache memory block size and the main memory block size was same. So the word field, the location of a word in a block, remained the same irrespective of whether the block was in the main memory or the cache memory. Similarly, here also the location of a word will remain the same whether irrespective of whether it is in the virtual memory or it is in the main memory. So the virtual address is divided into two parts. This is the virtual page number and this is the byte offset. I forgot to tell you one thing. The blocks in the virtual memory are called pages. The blocks in the virtual memory are called the pages and the blocks in the main memory are called frames. I'll repeat. Virtual memory has pages and main memory has frames. So now this virtual address, it has two parts. One is the virtual page number and one is the byte offset. Right? This again relates to the previous example. We had 20-bit virtual page number. There were 1024 kilo words in the virtual memory and we had 4 kilo words in the main memory. The size of one word was 1 KB. Right? So this byte offset will remain the same irrespective of whether we are talking about the virtual memory or the main memory. So now this 20-bit virtual page number has to be translated, has to be mapped into the 12-bit physical page number. Right? So that this 32-bit virtual address will get converted into a 24-bit physical address. Right? Again, the same whatever I have told you. Physical memory is broken down into groups of equal size called blocks. The group of address space of same size are called pages. Right? A page refers to the organization of address space. A block refers to the organization of memory space. Right? Now, this is, let us say, a virtual memory having 8 pages, and this is, let us say, a main memory, a physical memory which has 4 frames. Now, we are assuming over here that let us say page number 0 has been loaded into frame number 0, page number 2 has been loaded into frame number 1, page number 4 has been loaded into frame number 3, and page number 7 has been loaded into frame number 2. Now please pay attention. What it means is, suppose your CPU generates an address which is between 0 to 1023. That means the address of page number 0. Now the address of page number 0 can be found in the frame number 0. If the CPU generates an address between 2048 and 3071, which is an address of the page number 2, it can be found in the frame number 1. But what happens if your CPU generates an address between 1024 and 2047? This is page number 1 which has not yet been mapped onto any frame of the main memory. Now this is a situation which is similar to the condition where the CPU was generating an address and the address was not found in the cache memory. Now here also, when the CPU is generating an address which is not found in the main memory, that means the particular page has not yet been brought into the frame, this condition is called a page fault. This is called a page fault, and page fault means the particular page has to be brought into the main memory into a particular frame. Once again, there can be two possibilities. If there is a frame that is free, it can be loaded onto that frame, and if there is no frame that is free, then a page replacement algorithm has to be implemented. Now, within the page, we have a page table. Within a computer, we have a page table. This contains a present bit. Present bit means, it means that this particular page, whether this particular page has been loaded into any frame or not, right? This is the page number. Now, once again, now please pay attention. This is an important point. All the programs which are loaded in the virtual memory maintain a page table. All the programs which are loaded in the virtual memory maintain a page table. The size of the page table is equal to the number of pages in the program. Suppose a particular program is made up of 10 pages, then its corresponding page table will have 10 rows in it, right? These are the page numbers. This present bit tells me that which of the pages has been loaded into the frames. As was clear from the previous example, page number 0, page number 2, page number 4 and page number 7 have been loaded into frames of the main memory. And these are the frames where they are actually loaded. So page number 0 is loaded into frame number 0, page number 2 is loaded into frame number 1, page number 4 is loaded in frame number 3 and page number 7 is loaded in frame number 2. So this page table is maintained by each and every program that is loaded in the virtual memory. Now, how the address is mapped? Now let us say we have, let's take a simpler example, assuming that we have 8 pages in our virtual memory and only 4 frames in the main memory. Now, this is the page table, this is the page number, this is the presence bit, and these are the frame numbers. Now let us see how memory is mapped or how addresses are mapped. Line number will remain same. The byte offset obviously will remain same. So let us say the CPU generates this address. Out of this address, I will use the page number. I'll repeat, line number still remains the same. Now we take the page number and we check it in the page table. So page number is 101. Let me check it over here. So 101, we first check the presence bit. Presence bit will tell me whether this page has been mapped into any frame or not. So this presence bit 1 tells me that this page has been mapped into some particular frame. Now next we check which frame has it been mapped into. So the frame is 01. So we extract the 01 from here. Now with 01 and then we, so now we have got the frame number 01. We will use the same line number from the virtual address. So this becomes the new physical address. So this virtual address has been converted into this physical address. 3-bit page number has been converted into 2-bit frame number. Right? This is again a similar example. Now, as I said, page fault is the condition when the CPU generates an address and that address is not found in the main memory. What it means is the address relates to a particular page which is not present in any of the frames of the main memory. So this condition is called page fault. When page fault occurs, the CPU has to bring the particular page from the virtual memory to the main memory. And once again, let me repeat, if there is a vacant frame, then the page will be loaded into that. Otherwise, the CPU will have to need or implement a page replacement algorithm. There are many page replacement policies. One of them being first in, first out should be clear. The first page which was loaded in any frame will be scheduled for removal. So whichever was loaded first in the frames is scheduled for removal. Then we have least recently used. What it means is the page which has been used, the which has not been used for the maximum amount of time. The page which has not been used for the maximum amount of time will be replaced first. Then we have other replacement policies also, like LFU and other. Let's talk about these policies one by one with the help of an example. Let's first take the case of FIFO, first in, first out. Now this reference string, let's first understand what this is actually doing. This reference string is the page addresses being generated by the CPU. I'm not actually talking about the addresses of the blocks. We are talking about page references. What it means is the CPU is first referring to page number 7, page number 0, page number 1, and so on. And here we are assuming that we have a virtual memory which is having 8 pages 0 to 7 and a main memory which is having 3 frames. So when a reference to page number 7 was made, obviously there was a page fault. So this 7 was brought into the frame. In the very beginning, there is no page in the frame, right? So in the very first instance, when an reference to page number 7 was made, it was brought in the frame. Then a reference to 0 was made, it was brought into the frame. Again a page fault. A reference to 1 was made, again not available in 7.0, so it was brought into the frame. Then a reference to 2 was made, once again 7.01, so there is a page fault. It was brought first in, first out. Now if 2 is not present in the main memory and the main memory is now full, that means we have to replace any one page. So which page will be replaced? The page number 7, as it was first in. So 7 is replaced by 2. So now the main memory contains pages 201. Next, we are referring to page number 0, which is already present in the main memory. So this will not cause any page fault. Right? Next, we are referring page number 3, which is not present in the memory. So it will cause a page fault. And now which page will be replaced? After 7, we brought in 0. So 0 will be replaced by 3 and so on. So you can see here, if I'm referring 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. If I'm referring to 20 pages, so within referring 20 pages, I have 4 plus 6, 10 plus 15. A total of 15 page faults occur. While referring 20 pages, 15 times I had to suffer the page fault. Right? Let's see another example. Again, we are having a 3-frame virtual memory, and in this case, I'm using this 1, 2, 3, 4, 1, 2, 5, 1, 2, 3, 4, 5 as the reference string. Now, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Total 12 page references, and in referring to 12 pages, I had to encounter page fault 1, 2, 3, 4, 5, 6, 7, 8, 9. In referring to 12 pages, I had to suffer page fault 9 times. Now let me ask you a question. This was the case when I had a main memory having 3 frames. What will happen if I increase the number of frames? Obviously, if I increase the number of frames, more number of pages can be accommodated in the main memory. That means it should reduce the number of page faults. It actually does that, but there are exceptions, there are anomalies. If I take the same example with 4 frame, see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Instead of page faults decreasing, now instead of 9, I have 10 page faults. But this is not a general situation. This is an anomaly. This is a condition which is called Beladi's anomaly, and this does not always occur, but it might occur for some specific reference strings. So there are conditions or there are situations when increasing the number of frames might not actually decrease the number of page faults. Once again, let me repeat, this is not something that happens always. These are just anomalies. Next, let's talk about the LRU algorithm, least recently used algorithm. Right? So LRU means the particular page which has not been used for the maximum amount of time, for the longest period of time, that will be replaced. Again, let's take the same example. The first example that we took, 7 page fault, it is brought into the frame. 0, once again page fault, it is brought into this. 1 page fault, it is once again brought into the frame. Now 2 page fault, but the memory is full. So the particular page which was there for the longest period of time will be replaced. So which page has been there for the longest period of time? Which page has not been referenced, sorry, not present, not been referred for the longest period of time? That is 7. So that will be replaced by 2. Now please pay attention. 0 already present over here. So no page fault. Now we refer to page number 3, which is not present in the main memory. So there is a page fault. Now which page will be removed? See, if it was a first in first out, then 0 would have been removed. But just before referring 3, we had referred to 0. And just before referring to 0, we had referred to. That means the page which has not been referred for the longest period of time is the page number 1. And this is the page that will be actually removed. So 1 is removed and is replaced by 3, and so on. So you can solve these examples on your own. I suggest that you practice these 2-3 examples that I have given in the slides. Right? We can implement stack. We can implement LRU with the help of stack also. Right? Then we have counting based page replacement algorithms. The most commonly used of them being the LFU, least frequently used. Now, in case of least frequently used, or let us say most frequently used page replacement algorithm, we keep a count. Whenever a particular page is referenced, its count is increased by 1. And whenever we need to replace a page, in case of LFU, we replace the page which has the least usage count. That is least frequently used. Right? This is an example of that. These are the various references, and here we are maintaining the counts. So whenever a page has to be replaced, we choose a particular page which has the least count. And if there is a tie, we use FIFO to resolve a tie. What it means is, if there are 2 pages which have the same usage count and we need to replace one of them, then we choose it by FIFO. Whichever was brought in first will be removed first. There are certain numericals. I suggest you solve these numericals. Quite simple numericals. You can do them on your own. Now, virtual memory can actually be implemented in 2 ways. One is called paging and one is called segmentation. Whatever discussion we have had till now pertains to the paging method of implementation of virtual memory. Right? The second way of implementing virtual memory, the basic concept remains the same. The second way is called segmentation. The basic difference between paging and segmentation is, in case of paging, we divide the virtual memory or the main memory into equal sized pages. The size of each page is same, and the size of page in the virtual memory and size of page in the main memory is the same. But in case of segmentation, we have variable sized segments into which our program is divided, right? So a program segment, we may have different segments of programs, like we may have a code segment, we may have a data segment, we may have a stack segment, we may have an extra segment, and things like that. So a program segment will include the program's main function, data structure, utility function, etc., etc. So whenever the CPU requires a particular piece of information, that segment will be brought from the virtual memory to the main memory. So now main memory or the virtual memory will not be divided into equal sized blocks. The size of segments will vary. So variable sized segments will be brought into main memory as and when required. These are some main differences between the paging and segmentation. A page is of fixed block size, whereas a segment is of variable size. In paging, the hardware decides the page size, whereas the segment size is specified by the user. While writing the program, we decide what will be the size of the code segment, what will be the size of the data segment, and things like that. Paging technique is faster, whereas segmentation is comparatively smaller. In paging, the user just provides a single integer as the address, while in segmentation, there are many addresses that we need to provide. There is a starting address, there may a particular segment may be present at different locations. There can be links between those locations, right? So, and as we earlier talked about, page table was used for mapping the virtual address into the main memory address. Similarly, a segmentation table stores the segmentation data. So these are the details about the virtual memory. That brings us to the end of your memory organization unit. Once again, if you have any doubts, you can post them in the group and I will revert back to you. Thank you.